Okay, so next open method is Newton-Raphson method. Now the idea in the Newton-Raphson method is similar to the false position method. So remember, in the false position method we just take a bound, okay, with the initial guesses, and we draw a straight line from one to the other, and then we check the point where it crosses the x-axis. Now in the Newton-Raphson method we do the same thing. We basically make an initial guess for our initial point, and then at this point we draw a straight line, okay, and let's say that in both sides. And now we need to find where this line crosses the x-axis. So this is the basic idea of the Newton-Raphson method. But here there is another thing. Now let's look at this function, for example. We calculate the derivative, and derivative gives us the slope, okay, and the slope here is positive. Therefore we need to move in the negative side in order to find the position of the new root, new approximate root. So as a result we can calculate the root of a function from here. So f of xi minus 0 divided by xi minus xi plus 1. If we take out the xi plus 1 from here, we reach to this equation, and this is the formula or expression for Newton-Raphson method. So let's return back to the value that we are function that we want to find the root, e to the power minus x. This is our function. If we take the derivative of this function, so it is minus e to the power minus x, right? And x has a derivative of 1, so this is minus 1, and as a result we reach to this expression: xi plus 1 is equal to xi minus e to the power minus e to the power xi minus xi minus e to the power minus xi minus 1. Now let's look at the convergence. So in the first iteration the true error is 100%. Now for the second iteration we reach to a value of 0.5, and then error decreases 11.8. In the third one it is 0.147, and it goes down, and in the fourth iteration it is much smaller than 10 to the power minus 8. So basically the Newton-Raphson method converges very fastly compared to the previous techniques that we have seen, which we use for root finding. Of course, Newton-Raphson method has a pitfall similar to the false position method. If the derivative of a function is almost close to 0 then in a certain region of the domain, then you may have a trouble. And then the convergence is poor, so even if, or it may diverge, I mean, in some cases, as you see in the fifth iteration, the value is 33.88 with the initial guess of 0.1, even if the root is 1. So another pitfall is certainly it may not be convergent. For example, here we begin from a point, okay, and as a result we move in the negative direction because of the slope, and then we reach to this point, and in this point again you move in the positive direction, and as a result you are getting far away from the root step by step because of the second derivative. Here you see there is a turning point basically. What else? Again, because of the how the Newton-Raphson method works, basically Newton-Raphson method has a tendency of going to the minimum of the function, okay, because it uses the derivative, and if you move in the negative direction of the derivative, you will try to go to the minimum of the function, which we will see in detail in the optimization techniques. So basically we begin from the x0, you move to the here the derivative is negative, and as a result you move in this direction, and then this is where you reach, and then you will go to the x1 and then x2 and so on, and as a result you will you will be stuck at this point, and you will never be able to reach to the root because of the initial guess, which means that the initial guess is important in Newton-Raphson method in finding the root. Okay, what else? There may be some multiple roots, of course, but just think that you begin from a some value x0, that's okay. Then because of the slopes you may skip some of the roots. As you see, you may have multiple roots, and if you are at a point where the derivative is very small, okay, because of the numerical errors that you make, you may get far away from the root step by step. This is another thing. Again, you may reach to the local minimum, and as a result you will have a zero derivative. This will cause an overflow, as we see in the algorithm, and you will never be able to find the root also. So let's how we can apply the Newton-Raphson technique, Newton-Raphson method. This is the most widely used approach in root finding or solution of nonlinear equations, of course. Now we have seen how we did it. Basically we begin from an initial guess and we evaluate the function there. We take the derivative of the function. In fact, derivative of the function shows us the direction towards the maxima, so we want to go to the root. Therefore we drive the point in the opposite direction. So if the derivative is positive, so we drive the function towards the negative value, and we find the where the function intersects the x-axis. So we draw a line from the point because we know the slope there, we know the value there, value of the function, and we have the coordinate, and then we drive it to the point, and where it intersects, where it crosses the x-axis, and as a result we have a better approximation of the root. So let's see how we can do it by using MATLAB. Well, the last one was the fixed point iteration as far as I remember. Let's open it. Okay, so this is my fixed point iteration, and now I want to calculate the derivative of the function. Again, I will begin from an initial guess of 20 for the same function, but remember that our original function is my function 2, and this is f of r. So I modify it. I will open my function. So this was my function. I already calculated the derivative of the function, and I enter it to the I wrote a small MATLAB script for it, so it is here. I will open it as well, and here is my derivative of my function. You see, I calculate it and write a script on it. Now, okay, I will call dfr. So derivative of my function is equal to derivative of my function at point xr. That's also okay. Now I have my new value, old value, and I can now write xr. xr is equal to xr minus f of r divided by dfr, and then I will check the relative approximation error, relative approximation error, percentage error, and then I have the error value, I have the root value, and then I have my figures here. And let's run the script and let's check how many iterations does it need to converge, or will it work first. Here it comes. Now as you see, in 5 iterations I reached a value, and moreover after the 3rd iteration it's almost converged. So the first approximation is 13.6, and it goes like this. As you see, now let me have a look how the relative approximation error in percentage decreases. So in the 3rd iteration it is less than 1%, as you see, and then in the 3rd iteration it is less than 0.01%, much smaller in the 4th iteration, and so on. So it converts very fastly. But the point is, let's play with the plot command first, because I want to see both the function and its values on the same graph. So, or maybe it's better if we play with the plot first, So we have the X label, Y label, here X label, Y label. So let's change the line properties from the command line, because this line is not very clear and visible. I open the plot for help, or I already have the plot help menu. I already opened the help menu, and I will write here plot, and let's see it. Let's see the plots, commands for plots. Okay, this is what I'm looking for. Line spec 1, line spec 2. There are several examples here. I want to make it red. I will check the examples. Okay, here is a comment which fits to my needs, and it gives some examples. You see, line thickness is increased to 2. Marker size, there is a marker, you see. Marker edge color is blue. Marker face color is given in RGB. So I can take this. Line width is 2, so the line is dashed. It is green. So let me copy this part directly and modify it. So I put it here. So I have this one. I don't want to change the line type. It's not dashed. I want it continuous, but I want it red. So line width is 2. I don't need any marker size. Or yes, maybe marker size is okay. Marker edge color is blue. Marker color, I don't need it. I delete this part. Okay. I'm running it and see what's going to happen. I don't have the markers, even though I defined the so let's check the example again. I have GS, so the green with squares. Okay, so the second line defines here the marker shape. But I want O. Arrow. Okay, now let's see how it changes. Now it doesn't show the line. So I need to define a line. Yes. So these are my values. Okay. Okay, now we can do something else here, because I want to see the, let it remain so I want to see these root values on the function. So the numbers how I get close to the root. Now I will generate another function. So let's say that x values. So I will do another loop. Here at the end, let's say for index equal to 0.01. So this is my initial value. Sorry, let's say that this is x value for the function, and I will go until 20 with an increment of 0.01, and I say that index is equal to 0. I will close this for loop. Now I have the x value. Let's say that index is equal to index plus 1. xf, let's say x of function index equal to my function x value. This is the value of the function, by the way, f. I put a semicolon. Now x f index is equal to x value. Now these are the lines for the function. Now I will generate a new figure here, and I say that plot. Okay, and now I want to evaluate also functions at points of the root, approximated values of the root. So remember that the approximated values of the roots are the root value. So I will generate another do loop here, but let's check what I have for. So there is the size command. Now I want to get the size of the root value. Let me check the help for it, how it works. Here it comes. So it gives us the size. Of array, and whether we will see how it's going to work, whether it's okay or not. So this will be the n, let's say. Therefore I will generate another do loop here, but this time index I will use here, 1 to n. I don't need the increment of index because it will increase one by one. Let's say that this is approximated rule AR. My function is the root value index. Yes, because I want to evaluate. This is XAR, and now this is root value index. Okay, now I have the root value, approximated root values, and I have the values of the functions there. The original functions, and now I have the figure. So first I have xf, f, then xar, far. Now I will define the property for xar and far. Or first let's run this and then see how it's going to happen, what's going to happen. Let's enlarge it. Now it's not clear here, but certainly I have a green line here. So let me close this box. And let's copy these lines from here. And paste here. Now I don't want any line for my root values. I just want to see the marker. So the title is my function. X label is X, and this is Y. Now here the point is this applied to the both lines anyway. So let's define a line color for the first one. So I just put here another comma and define it as red. And the line is continues. Here it comes. Of course, all the markers are almost very close, so let's magnify it. I have to pan it. There's a mistake in the code. Why it gets only 1 point? Let's check it. Index is equal to 1 to n. Let's debug it. I put a breakpoint here. So n is an array. So it's 1 to 5. And in order to get the second value, I need to write here n2, because as you see, it is the second. So it gets the size of the error. It's 1 to 5 array, and it automatically gets the first one, and as a result it makes a mistake here. Okay, now I can exit from the debugging mode. I have to clear the breakpoint. Now let's run it. Here it comes. Now let me zoom. Okay. So these are the values. So after the third iteration, we don't see the points because they are very close. So these are the this is the first guess, and the second one, and the third one. It goes like this. So in 5 iteration you reach to the root.